All right, so with universal gravitation, it's very common to get a net force problem along with that, okay? So if we're imagining that Earth and the Sun and the Moon are at least frozen in time for this instant, because obviously they only look like this for a very short period of time, okay? We want to find the net force acting on the Earth. Well, there are two forces pulling on the Earth, okay? There's the force of gravity between the Sun and the Earth that's pulling the Earth that way, and there's the force of gravity between the Moon and the Earth that's pulling the Earth towards the Moon. Okay? The net force acting on the Earth is obviously towards the Sun, or the Earth wouldn't orbit the Sun, but we need to find out what that is. Okay? So first thing we want to do is calculate the force of gravity between the Sun and the Earth. So that'll be 6.67 times 10 to the minus 11, the universal gravitational constant, times the mass of the Sun, 1.99 times 10 to the 30, times the mass of the Earth, 5.98 times 10 to the 24, divided by 1.50 times 10 to the 11 meters squared. Okay, that'll get us our force of mutual attractive force between the Earth and the Sun. We're simplifying it here and saying it's the Sun pulling on the Earth. All right, so we got 6.67 e negative 11 times 1.99 e 30 times 5.98 e 24, and then we divide that by 1.5 e 11 squared. Okay, so we're getting that the attractive force of gravity between the Earth and the Sun is 3.53, and actually all of these numbers are givens from, or constants from your formula sheet. What does that mean for significant digits? Yeah, you have basically unlimited significant digits. Okay, we consider all of those numbers to be absolute on your formula sheet. They're not, but we consider them to be. Okay, so we'll leave it at that big number for right now. I'm going to abbreviate it on the board here as 3.53 times 10 to the 22. Okay, so that's the mutual attractive force. But from the Earth's perspective, that force is which direction?
One towards the Sun, and second, if all the numbers that we have are given values, that means every single number has an infinite amount of significant digits. How do we write the answer?
You choose. Yeah, there's no right or wrong number of significant digits on a question like that.
So we could do what?
Well, I wouldn't. I mean, pick a number that kind of makes sense. Like, I'll show you what I mean on this question, because obviously this is a situation where that applies. Okay, so this would be towards the Sun from the Earth's perspective. I don't even know what that last word says. Sud? Sun. There we go. Okay, and then I've got to do a force of gravity between the Moon and the Earth calculation. So that'll be 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24 times 7.36 times 10 to the 22 divided by 3.85 times 10 to the 8 squared. Okay, so I'm going to do this and maybe save myself some time. Oh, no, I didn't save myself any time now. No, I didn't. I screwed it up.
Yeah.
Okay.
Like, 22 at the end.
Oh, well, okay. Yeah.
If you just go back and review some.
That's okay. I'm just gonna type it out because I'm at that point now. Okay, so there's the force of gravity between the Earth and the Moon. 1.98 times 10 to the 20 newtons. And from the Earth's point of view, that's toward the Moon. Okay, how do I find the net force?
Would you just do like, so like F net equals like the force like between Earth and the Sun, like plus negative version of the Earth and Moon?
Exactly. Vector sum of all forces. Okay? That is all I have to do to get the net force. So I'm going to go F net equals force of gravity between the Sun and the Earth plus force of gravity between the Moon and the Earth, but that one's going to be negative because it's in the opposite direction. So we'll have our 3.53 times 10 to the 22 plus negative 1.98 times 10 to the 20, okay? And that'll give us our net force, net force acting on the Earth. So I will take that number, and I'm going to subtract that number. Okay, so the net force acting on the Earth, and I'm just going to say 2 decimal places here, okay, 3.51 times 10 to the 22 newtons towards the Sun. Okay, I can't tell you how often on a unit exam when I put a question like that on there that people don't put a vector on the answer. And so by the time I'm done marking 2 class sets worth, I'm like writing it in blood red capital letters angrily. Okay, it's a vector quantity. Let's not forget that net force is a vector quantity, so we don't lose a mark on there. Okay. All right, questions on how that one worked? Okay. So I mean, this could be the other way too, right? It could be for a solar eclipse, and then the moon would be between the Earth and the Sun, and then they'd both be pulling the same direction. And this is why the Earth's wobbling back and forth in its orbit. As the moon goes around it, it's constantly pulling the Earth back and forth, okay, in different directions. So even though we say, yes, the Earth's orbit is generally elliptical, it actually goes like this all the way around the Sun, back and forth, back and forth. Okay, so this is the solar eclipse one here, number 1. And this one here, with it at a right angle, okay, you got to do like the vector addition. You got to put them tail to head. Okay? And what you find is it basically is almost negligible. The angle is so incredibly small. Okay? It's 0.3 degrees. Okay? Now, I know it doesn't seem like much. When we're talking about astronomical distances, 0.3 degrees is still something. All right, let's talk about satellites. So we can find lesson 10 in your notes package. That is what we're going to be going over. So yesterday, we calculated the speed of the moon as it orbits the Earth. Okay, that was a satellite question. In any satellite question or satellite problem, the centripetal force causing the satellite to stay in orbit is provided by what force? What provides the centripetal force? Gravity. Yeah. The force of gravity is what makes something orbit something else. Okay? Unless we're talking about electrons orbiting the nucleus of an atom, in which case that's electromagnetic. So different. But when we're talking about planets and stars and things like that, we're talking about force of gravity. So we need to understand that satellites obey uniform circular motion laws. So back to uniform stuff. The speed will be constant throughout the orbit. Simplified, of course. And we know it's not really, but simplified. Okay. Understand that for all orbiting bodies, gravitational attraction between the two bodies provides the centripetal force. That means we're using Newton's universal law of gravitation, or big FG. And we need to learn that any orbit is achieved by making sure a body travels far enough that the distance it falls is accounted for by the curvature of the body that it orbits. Okay, so Newton had this idea. And by the time Newton was kind of late in his career, he was so well thought of in the scientific community, he didn't even have to do real experiments anymore. He started doing thought experiments, which means he thought up something in his head and then wrote it down. And people went, okay, you're pretty smart, so yeah, we won't fact check that. Okay. Now, on the other side of that, there was absolutely zero way to do this experiment or fact check it, okay, at least in Newton's time. Newton had this idea that you could make something go all the way around the Earth, in other words, orbit the Earth, provided you make it go fast enough, because the Earth was round. See, they knew that back then. Okay. So, since the Earth was round, and still is, you could shoot something really, really fast, like out of a cannon, for example, a really, really powerful cannon, off the top of a very tall mountain. And as long as it would travel about this far, about 8 kilometers in 1 second, the amount it would drop due to gravity, which is 4.9 meters, by the way, 4.905 meters, that's how far you have to travel for the Earth to curve away 4.905 meters. Okay? So the curvature of the Earth is that the Earth's curvature in general drops 4.9 meters over an 8 kilometer distance. Okay? So, if I can make something travel at 8 kilometers per second near the Earth's surface, it will orbit the Earth. So if I'm standing on top of Mount Everest and I carried a big cannon up there, because somebody would do that, okay, I could shoot the cannonball and then have it come all the way around the Earth. So don't stay there. Okay. But obviously, no, that's not going to work. You can't make something go through the Earth's atmosphere at 8 kilometers per second. Okay, it would be absolutely annihilated by the heat due to friction. Okay, that's why things burn up when they re-enter the atmosphere sometimes.
Assuming that the cannonball was made out of a special material that wouldn't burn up, would this still be true?
This is all theoretically true. Yeah, Newton's thought experiment is totally valid. It's just not replicable in reality. Okay, but this is the basis for all satellite motion. Okay? As long as we can get something to go fast enough, it will orbit. So what we do is we build rockets and we move things outside of the Earth's atmosphere where friction is no longer a factor. Okay? And of course, the further away from the Earth you get, the slower you have to go in order to stay in orbit. Okay? Like we saw yesterday, the moon moves at 1 kilometer per second. It's quite a bit further away. Okay? This has to move at 8 kilometers per second because it's very close. Gravity is much stronger between the two, okay? And so it wants to fall a lot faster. Okay? You put something up in orbit, okay, like where the International Space Station is, low Earth orbit, and it still has to move pretty fast, okay? But not 8 kilometers per second anymore because obviously it's further from the center of the Earth. Okay? And that's the important distance, by the way. Center to center is still the orbital radius when we're talking about a satellite, still center to center. All right, everybody okay with that? Okay, so there were lots of kind of diagrams of what this would look like. Okay, if you put somebody on top of a tall pillar and they, throw or hit something really fast, it would go. Okay, it's basically a projectile. Okay? If you don't hit it fast enough, it follows a projectile arc that encounters the Earth. Not quite fast enough, it goes a little further, but still encounters the Earth. Okay, a little faster, still encounters the Earth. If you hit it fast enough, that projectile arc becomes a circle that never encounters the Earth, because you're going fast enough that the distance you fall is equal to the distance the Earth curves away, and you never change your radius to the Earth's center. Right? So, this was figured out, obviously, very early on. Newton had this figured out. But making it work was the technological challenge, okay, during the space race, okay, back in like the 50s and 60s. Right? So you had the Soviets and you had the Americans, and they were competing to get into space first. They were competing first to break the sound barrier, then to get into space, then to orbit the Earth, and then to get to the moon. Okay? Oddly enough, the Americans lost 2 out of the 4 of those. Okay? They won the sound barrier one, and then they lost first to space. Actually, they lost first object to space, first person in space, first orbit of the Earth. They lost all of those. But they got to the moon first. That is a pretty big deal. So, back during that time, course, the height of the Cold War, when the Soviets got the first object to orbit the Earth, it was Sputnik, okay? Like a chrome ball with 4 antennas coming out of it, okay? And it orbited the Earth and it beeped. Okay? It broadcast a simple radio signal that just went beep, beep, beep. Terrified people. People were mortified. The Soviets made something orbit the Earth. If they can get something into orbit, like a satellite, like this thing that beeps, they could put a bomb in orbit and then it could fall on us. Oh my God, we're all going to die. Okay, that was the thinking of the time because it was the height of the Cold War. And so, of course, the Americans had to get to that point as well so that they could have a system of delivering, a weapon over that kind of distance. That's how, intercontinental ballistic missiles essentially became a real thing. Okay? So, yeah, that little chrome ball scared the crap out of everybody, okay, when it first went into orbit. And then, it got easier and easier to get people into orbit, so then the challenge became, let's go to the moon. Okay, well, that's an entirely different thing. Okay, so a satellite that's in orbit is always the same height above the Earth and moving with uniform circular motion. Its centripetal acceleration is still v squared over r, okay, its centripetal force is still mv squared over r, but it's provided by gravity. Okay, there's different kinds of orbits as well. Okay, there are bound orbits, okay, that are circular. There are bound orbits that have the satellite change its distance to the Earth's center. Okay, there's high Earth orbit, low Earth orbit. There's all kinds of different ones. And then if you have, if something goes fast enough, it will achieve escape velocity, which means it goes so fast that its radius quickly becomes infinite. Okay, and so it does not stay in orbit. So if you're wanting to send something somewhere else, you have to make it go even faster than you would just to put it in orbit. Okay? So we have special rockets for putting things in orbit and special rockets for making things go much further than that. All right, so this we talked about yesterday, okay? Where big FG, so big G times the mass of the Earth times the mass of the satellite over r squared equals the mass of the satellite times speed over r. Okay, we talked about that one yesterday. Sometimes with a satellite, rather than wanting to know the speed, a question may want to know the orbital period. So how long it takes to make one orbit. And sometimes it doesn't give you enough information to do that in 2 steps. It doesn't give you enough to go, all right, I'll solve for v, and then I'll go v equals 2 pi r over t and get t. Sometimes they don't give you enough information, so you have to substitute. Right? So substitution is going to look like this. So normally I would have FC equals FG, and that would be mv squared over r equals big G times mass over r squared. So if a question gives, let's say, it gives me the orbital period and asks me for radius, okay, it might look something like this. So it would say, give me the mass of the satellite, it would give me the mass of the Earth, obviously because I always have that, and it would give me the orbital period, and then ask me to find radius. So I would have this number, I would have this number, okay, these two are the same number, then I would have the mass of the orbital body. So there's the orbiting body and the orbited body. Okay, so the mass of the satellite actually cancels. I don't have V and I don't have R. So how do I solve for R? I don't seem to have enough information here.
Can't you manipulate that thing in a way that it equals R and substitute that for R?
I do have to do a substitution, yes. But I substitute for V. Okay. This is the other formula that calculates V. Okay? It has one of the things I was given in the question and the thing I was looking for. It eliminates my need to know this. Okay? Everyone with me on that? So I need to put this formula here. I need to superimpose it basically onto that formula. Now in that formula, V is squared. So what do I need to do with the formula? And squared. Okay, what's 2 squared?
4
4. What's pi squared?
pi
Pi squared. Okay, and same with r, and same with t. So there we go. There's the formula squared. That wasn't very hard. Okay, now all I have to do is take this and jam it into this formula. Okay, which, I mean, it sounds exactly like what I'm going to do. I'm literally just going to jam it in that formula. So I'm going to leave m, and I'm going to leave r. Okay, those aren't going to change. They're still there. And I'm going to put this in instead of v. So 4 pi squared r squared over t squared. What do I do with those r's? Yeah, okay. So the one on the bottom goes away, and the square goes away. Now I've substituted. Now I've put into that formula something I was given in the question, and I still have the thing that I'm looking for. So now I can manipulate and solve for r. Now the weird thing about this is when you manipulate and solve for r ends up being cubed. Is that okay? To solve for it, then you'll have to take the cube root, which you can do in a calculator. Okay? But that's substitution, and you will have to do that at some point as we work on satellite motion problems. Okay? We will have to do that substitution. All right, so that's what this was showing here. Okay, we just put it in there. So the different orbits here, guys, if you have like polar orbits, obviously they go over the poles. You can have equatorial orbits. You can have basically any angle is going to be a valid orbit. And then you can have geosynchronous orbits. What's the period of a geosynchronous satellite? 1 day. Okay. In order for a satellite to stay over the same point on Earth, it has to have the same period for an orbit as Earth has for a rotation. That way it keeps staying over the same spot on the Earth all the time. Okay? We didn't always have geosynchronous satellites because geosynchronous orbits are a lot higher than low Earth orbit. So most of our first ventures into space, most of our first satellites, communication satellites, etc., were in low Earth orbit because that's what we could effectively put into orbit. The problem with that is they don't stay over the same spot. So early satellite TV, okay, worked a lot different than modern satellite TV. Okay? Anyone ever seen like a really old satellite dish? Okay? Like a modern satellite dish is about this big. Okay? An old satellite dish, they were more than 6 feet across. Okay? They took up half your yard if you had them. You couldn't mount them on the roof. Okay? And in this area, they'd have blown over all the time. But the problem with them is that they would have to actually move. Okay? A modern satellite dish just points at the sky, and you orient it a little bit just so that it generally catches a few satellite signals, and that's it. Old satellites tracked. Old satellite dishes tracked. They would literally move around to track a satellite. Now, that's problematic because motors wear out. Okay? But it's also a problem if you're watching the Stanley Cup final and your satellite dish has been following a satellite, tracking it and keeping the signal, and then the satellite goes over the horizon. That usually happens in double overtime, just as somebody is skating towards the net. Okay? So then, your satellite dish has to go and go all the way back to the other side of the horizon to catch the next satellite as it comes over the horizon to reacquire the signal. That's how old satellite TV used to work. Okay? It was highly inconvenient. Okay? It was also, if you bought a dish, basically free. But it didn't work like modern satellite television where satellites are geosynchronous and your little dish just points up a section of sky where some satellites are likely to be located. And that works way better. It's far more reliable. And doesn't require a giant saucer in the backyard. So, that's what the purpose of geosynchronous orbits are for, is to keep something in position where it can be constantly used. Most satellites that we use for communication are like that. Okay? The satellites that aren't are ones that are trying to actually see different parts of the Earth. So research satellites and things like that, their orbits can be modified. Spy satellites, obviously, their orbits can be modified all the time. Oh, incidentally, if I ever ask a question about a spy satellite, by default, which planet is it orbiting? Earth. Because I often get that question when I say a spy satellite is in orbit. And they're like, which planet? Like, who else are we spying on? Okay? Not spying on the Martians. Okay, we're just here, yeah. Okay, so let's have a look at what do we got here for time. All right. That one we did yesterday. All right. I want you guys to try these two. Okay, so we got Neptune is a satellite of the sun, obviously. Okay, and then this one here is about one of Uranus's satellites, okay? Or moons. Okay, just because we're starting to run a little bit short on time here. For question number 1, we're solving for the speed of Neptune. Okay, now what did they not give you? They didn't give you Neptune's mass. They didn't give you Miranda's mass in the second one either. Why? It cancels out. Yeah, the mass of the satellite always cancels because all things at that point would fall at the same rate, regardless of their mass. We are, after all, talking about an acceleration due to gravity. And we already know that all things fall at the same rate due to gravity, regardless of their mass. Okay, so that's why mass cancels. So on this one here, okay, we've got mv squared over r equals big G times the mass of the sun over r squared. Okay, so the mass of Neptune cancels. We bring the r over here. It cancels the square on the bottom, and then we take the square root of that to get the speed of Neptune as it orbits the sun, and it's 5.43 times 10 to the 3 meters per second. Okay, to manipulate for radius, right, we would have mv squared over r equals big G times the mass of Miranda times the mass of Uranus over r squared. Okay, so if we're trying to, whoops, I don't know why I put a square root over that. Okay, so we bring r over here. Okay, so r squared comes over here. It's going to cancel off with that. We divide the other two over. Mass of Miranda cancels. V squared ends up over there, and we're solving for r. Okay, everybody all right with that? Okay, what kind of name is Miranda for a moon? Okay, you guys know that there's a naming scheme. If you discover a moon around a planet in the solar system, you cannot name it whatever you want. There's actually a rule, or rules, for naming moons in our solar system. I mean, for Earth, it's easy. When you only have one moon, you know what to call it, the moon. Okay, but for Mars, its moons are Deimos and Phobos, because Mars is the god of war, and the companions of war are fear, Phobos, and panic, Deimos. Okay? For Jupiter, this is a weird one. Jupiter is named for Zeus. All of the moons of Jupiter are named for the lovers of Zeus. And that's a lot. It's over 60 and we're not on the names. Okay? Zeus, not necessarily a nice guy. For Saturn, they all have to do with time and the Titans. Okay? So they're all named for Titans. For Uranus, they're all Shakespearean characters. Miranda is from The Tempest. She is the daughter of Prospero. Okay? And then for Neptune, they all have an aquatic theme. Okay? So Triton is the weapon, the trident, okay, that Neptune would carry. Okay? And all the other ones have some sort of aquatic theme to them. Okay? Or they are companions of Neptune of some type. Okay? And then for Pluto, they all have to do with the underworld. So Pluto's main moon is Charon, okay, Charon, and that is the boatman that takes you across the river Styx to the underworld where Pluto is. I tell you, people got to know their mythology big time if you want to name a new moon in the solar system. So there you go, piece of completely useless trivia.
Who's going to stop you?
Well, actually, the Union of Astronomers can stop you. Okay? There are rules for naming. Okay? Like if you discover a star, its technical name goes for what sector of the galaxy it's in. All right, see you guys. Have a good weekend.